projects. In this video, we are going to explain about a project entitled as Research on Hybrid Architecture Neural Networks for Time Series Prediction. So, before getting into the video, let me give you a brief description about the project. The project focuses on developing and analyzing neural network models that combine different architectures such as CNN and LSTM to improve the accuracy of predicting future values in time-based data. These hybrid models aim to capture both complex pattern and temporal relationships, making them more efficient for forecasting tasks in areas like finance, weather, and energy. Coming to the abstract, this study introduced a hybrid neural network model called TCN-MLP attenuation to predict agriculture products prices more accurately. Since prices are affected by many complex factors like supply-demand changes, seasons, and weathers, traditional methods often fail to give precise forecast. The proposed model combines three techniques: TCN to capture time-based pattern, MLP to learn complex relationship, and an attenuation mechanism to focus on the most important time steps. Using US avocado price data from 2015 to 2023, the model achieved higher accuracy and better generalization than traditional and transformer-based models. Overall, the results shows that this hybrid approach is powerful, reliable, and flexible, making it suitable for predicting prices of various agriculture products. Coming to the existing system, most current situations that predict agriculture product prices use traditional methods like Aramia, exponential smoothing, or support vector regression. These methods assume that data follows simple, linear patterns, but in reality, prices change due to more complex factors like weather, season, and demand, which makes prediction difficult. Newer deep learning models like RNNs and LSTMs and GRUs can handle time-based data better, but they have problems such as being slow, needed lot of computing power, and sometimes losing important information. Transformers model have also been used recently and perform well on large data sets, but they still struggle with detailed time-based patterns. Because of these issues, existing systems still finds it hard to make highly accurate or reliable predictions for real agriculture markets. Coming to the proposed system or base paper work. The proposed system introduced a new hybrid deep learning model called TCN MLP attenuation to make agriculture price forecasting more accurate and reliable. This model combines three powerful patterns: TCN, which learns time-based patterns from past data; MLP, which handles complex relationships in the data; and an attenuation mechanism, which focuses on the most important factors affecting prices. It also uses the Adam W optimizer to train the model efficiently and improve performance. When tested on US avocado price data from 2015 to 2023, the system performed better than traditional methods, giving more accurate results and working well even for other products like strawberries. Coming to the data set. In the study, we use the avocado price and sales volume 2015 to 2023 dataset from Kaggle, which contains detailed information about avocado prices and sales trends across different regions in the United States. The data come from the Has Avocado Board and includes daily or weekly reports for several important features. Some of these features includes the date, average price of avocados, total sale volume, and specific PLU codes like 4046, 4225, and 4770, which represents different avocado sizes. The dataset also includes information about bags sold in various size categories, the type of avocado, whether it's conventional or organic, the year, and the region where the sales occurred. This dataset covers data from 2015 to 2023, giving a long time span that captures both seasonal and regional varieties in avocado prices and sales. Because of this, it's perfect for time series forecasting, allowing us to study how price changes over time due to factors like season, demand, and location. By providing such detailed and well structured information, this dataset is ideal for training and testing advanced predictive models, especially our proposed TC and MLP attenuation model to better understanding and predict agriculture price movements. Coming to the novelty or extension or improvement or enhancement. As an extension of this work, we implemented handled the data by removing null values, eliminating duplicate records, and applying normalization to ensure consistent and accurate input for the model. To further enhance performance, we added a voting regressor which combines multiple models to improve prediction accuracy. This approach achieves an impressive R-square score of 93%, showing strong predictive capability. In addition, we used explainable AI techniques like LIME and SHAP to understand how each feature contributes to the prediction results. These tools helps making the model decisions more transparent and interpretable, showing which factors most influence avocado price prediction. Coming to the flow of the work, firstly, we need to import the packages. In this step, we import all the required Python libraries and deep learning frameworks like TensorFlow or PyTorch. These packages help with data handling, visualization, pre-processing, model building, and evaluation. Next, exploring the avocado sales dataset. Here, we load the avocado prices and sales volume 2015 to 2023 dataset and explore its structure. We check the columns such as date, average price, total volume, PLU codes, type, year, and region. This steps helps us understanding what kind of data we have and identifying any issue before processing. Next, data pre-processing. Data pre-processing is a key step to clean and prepare the data set for modeling. It includes several sub-steps like removing the null values. Missing values are identified and removed by replaced to prevent errors during the model training. Remove duplicates. Duplicate records are deleted to avoid bias in the results. Outer line screening. Extreme or unusual values that can distort the prediction and detected and handled. Data aggregation and transformation. We group and transform data into a suitable time series format, such as daily or weekly averages. Then normalization by mini-max scaler. The numerical values are scaled between 0 and 1 to improve models' convergence and performance. Dataset division. Time-based split. The dataset is split chronically into training, validation, and testing sets. Sliding window segmentation. A window-based approach is used to create input-output pairs for time series learning. Then, cross-validation strategy. We use time series aware validation to evaluate model performance on unseen data and temporal correlation analysis. This step checks relationship between time-based features to ensure useful patterns are captured. After data pre-processing steps, we have data visualization. In this module, we use plots to understand data trends and patterns, like normalizing the data average prices shows how avocado prices change over time after normalization, and correlation matrix displays the relationship between features, helping to identify which factor influence prices most. Then, building the regression models. We develop several machine learning and deep learning models to predict the prices, like MLP, multi-layer perceptron, TCN, temporal convolutional network, MLP plus TCN, TCN plus MLP plus attenuation, LSTM, long short-term memory, GRU, gated recurrent unit, CNN plus LSTM, transformer, informer, Aramia, which is known as statistical model, SVM, support vector mission, XGBoost, extreme gradient boosting. And as an extension model, we applied LSTM plus GRU that combines the strengths of both models to better capture time dependencies. We also use voting regressor, combines multiple models prediction to improve overall accuracy. Next, training the model. In this step, each model is trained using the pre-processed dataset. Parameters like learning rate, batch size, and epochs are optimized. The training process teaches the model to learn patterns and relationship in the avocado price data. Then, model comparison and evaluation. We evaluate odd models using performance metrics such as MSE, mean squared error, RMSE, root mean squared error, MAE, mean absolute error, R square score, coefficient of determination, MAPE, mean absolute percentage error, and Pearson correlationship. These metrics helps us compare model accuracy and select the best performer. Next, comparison graphs. We visualize comparison charts showing how each model performance based on their evaluation metrics. These graphs make it easier to identify which model gives the best results. Next, save the best trained model. Once the best model is identified, it is saved for future use. This allows us to deploy the model without retraining it each time. Next, explainable AI visualizations. Finally, we use Lime and SHAP to interpret the model's prediction. These tools shows how each features affects the predicted price, making the model's decision more understandable and transparent. The algorithms used are MLP, TCN, MLP plus TCN, TCN plus MLP plus attenuation, TCN plus MLP plus attenuation plus by LSTM, LSTM, GRU, CNN plus LSTM, Transformer, Informer, Aremia, SVM, XGBoost, LSTM plus GRU, and voting regressor. Coming to the requirements, we have both hardware and software requirements. Hardware requirements: operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements: application framework is Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3. Technologies which we use to build the front-end are HTML, CSS, JavaScript, and Bootstrap. To execute the project, first we need to open the code folder, which contains the project source code files. The project code folder is a complete package of your project's code base, containing everything needed to deploy, test, and develop your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files. Template folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations, such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are the model files which contain algorithm information which will be loaded into the project code during the runtime. Notebook.ipynb file. This is a Jupyter Notebook file which contains a combination of code, graph, and outputs all in one place. It allows user to write and execute code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Coming to the execution of the project, copy the path of the code folder from the address bar of the file explorer. Open Anaconda prompt. Use the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address and port. Copy the link provided by the framework and paste it in any web browser. I prefer Chrome. The home page of the project should now be displayed in the browser. This is a front-end built using Flask framework. So, this is a web page of the project displayed on the browser. In this page, we have Home button and Get Started button. Now, click on Get Started button so that the login HTML will be opened. Here, we need to give the details and create an account for user authentication like username, full name, mail ID, mobile number, and password. Then click on Create an account so that all the given details are stored in signup.db and the login HTML will be opened where we need to access the application by username and password. Then click on Sign In so that the prediction page has been displayed. In this, we have Home button, Data Visualization button, Notebook button, and Logout button. Now, click on Try Prediction so that the price forecasting form will be opened. Here you need to give the input values for prediction like price on day 1, day 2, day 3, day 4, day 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. Now click on prediction of next day price. Based upon the given inputs, the prediction results has been displayed like $2.0768, like next day forecast. How the prediction has been worked in the sense by giving the pattern recognition, trend analysis, market indicators, and historical correlation. And here we have the next steps like we can make another prediction or we can view the data visualization. Now click on data visualization. Data visualization means it representing the data in graphical or visual format such as charts, graphs, maps or dashboards so that patterns, trends and insights can be easily understood. So first we have normalized daily average price. This graph shows how the daily average prices changes over time after being adjusted to a common baseline. It highlights relative trends or growth rather than actual price values. On the x-axis, we have the number of years like 2015, 16, 17 and so on till 2024. And on the y-axis, we have the normalized price. Then close this. Next, we have feature correlation heat map. This graph shows how strongly different features or variables are related to each other. The color indicates the strength and direction of this correlationship. Next, we have MSE graph. MSE stands for mean squared error. It measures the average of squared prediction errors. Next, we have RMSE graph. RMSE stands for root mean squared error. It is a square root of MSE showing error in original units. Then we have MAE graph. MAE stands for mean absolute error. It represents the average of absolute differences between predicted and actual values. Next, we have R-square graph, which is known as coefficient of determination. It shows how well the model explains data variance. And next, we have MAPE graph. MAPE stands for mean absolute percentage error. It shows average prediction errors as a percentage. Next, we have Pearson graph. Pearson correlation coefficient graph. It means the linear relationship between the predicted and the actual values. And at final, we have SHAP explainable AI graph. It shows how each feature contributes to its model prediction using SHAP values. It helps explain which feature most influence the model output and whether their impact is positive or negative. Then click on Logout. So finally, hybrid architecture neural network combines models like CNN, RNN and transform the improved time series prediction accuracy. They capture complex pattern and long-term dependency more efficiently. This approach enhances forecasting in areas such as finance, healthcare, and climate analysis. This is all about your project. Thank you.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.